始めさせていただきます。続いてのご講演は、アレクセイ・コノプリョフ先生。先生のご紹介をさせていただきます。アレクセイ・コノプリョフ先生は1977年にモスクワ州立大学を卒業し、科学そして放射線生物学の博士号を取得されております。その後36年間にわたり環境科学の分野、特にチェルノブイリの事故に由来する放射性各種の挙動、そしてその予測に関する研究に従事されております。2013年からは福島大学環境放射能研究所にて特任教授としてご活躍されております。放射性セシウムの挙動に関する土壌、水源を中心とし、チェルノブイリ事故と福島の事故との比較分析をされております。今日の先生のご講演タイトルはRadioactive Water Contamination and its Dispersal in South Ural Manyak Area Review ということで、麻薬核施設からの放射線漏洩と環境影響についてお話しいただきます。それではコノプリョフ先生、お願いします。
ありがとうございます。こんにちは。How to manage this?
I'm not really good at PC.
Okay.
This one.
Okay. So, my name is Alexey Konoplev. Actually, I'm a Russian radio ecologist working nowadays here in Fukushima University in the Institute of Environmental Radioactivity. And immediately after the Chernobyl accident, I was involved in emergency response and research on radionuclide transport and prediction, providing the prediction of radionuclide contamination of water experience for their planning and carrying out the research. So, this is the outline of my talk. So, first I will talk about the Mayak production and its radioactive. So-called Kyshtym accident or South Ural accident taking place in 1957. Then we will talk about the Lake Karachay and its desiccation in 1967. So we'll talk about the Teche River and its floodplain. Then we go to the Viga River system, which is the Teche, Iset, Tabol, Irtysh, Ob River system, and which actually influenced by discharges from the Mayak Production Association. I will tell about the remediation activities in South Ural contaminated area and some final messages. So here you can see the map with the place we are talking about. So this is actually Russia. Japan is over here. UK and Ireland is over there, Scandinavia. So the place we are talking about, Mayak Production Association, is located in South Ural, nearby to the border between Europe and Asia. And Mayak is situated on the upper reach of Kecha River, which is the part of a bigger river system. Here you can see the more, let's say, illustrative picture. Mayak is over here on the Kecha River. Kecha enters to the Isit River. Isit River enters to the Tabol River. Tabol River goes join the Irtysh River, and finally they join Ob River, which is entering the Kara Sea of Arctic Ocean. So the whole such a river system with the length much longer than 1,000 kilometers is influenced by the discharges actually of Mayak. So the Mayak Production Association belongs at the moment to the Russian State Corporation on Atomic Energy, Rosatom, and is located in the northern part of Chelyabinsk region, near the towns of Kyshtym and Kasly. So here is Mayak. The red area is the production site of Mayak. Here is Kyshtym, Kasly, and Chelyabinsk is over here. The enterprise was established at the end of the 1940s to produce and process weapons-grade plutonium. So in this sense, this is quite similar to Savannah River and Sellafield and stands in this series. So although Mayak is still engaged in military work, the production of weapons-grade plutonium ceased in 1987, and the enterprise has increasingly directed its technical potential towards non-military applications. By the middle of 1948, the first military reactor was installed, and this military reactor was in operation and generated plutonium for 39 years. It was eventually shut down in 1987. So here you can see the detailed map of Mayak location. The health protection zone is over here, and this zone is called observation zone. So any agricultural practice and housing in the health protection zone is forbidden, and but it's allowed outside. Unfortunately, during the development of Mayak, a combination of major errors in judgment and technical failures caused severe environmental contamination in the vicinity of the Mayak. Major incidents included, first, direct discharge of intermediate liquid waste to the Kecha River from 1949 to 1956. Secondly, discharge of liquid waste to Lake Karachay, starting from 1951. Then the Kyshtym accident happened in 1957. And in 1967, the wind transport of contaminated sediments, which was dried and desiccated from Lake Karachay, took place. So, therefore, when we are talking about the South Ural radioactive contamination. We should distinguish different sources or different processes. Some of them were immediate impulse releases. Some of them were long-term chronic releases. So here on the picture you can see still Mayak site, and the Lake Karachay is over here on the production site of Mayak. Kecha River goes over here, and here you can see the Eastern Ural radioactive trace, which was as a result of so-called Kyshtym accident. But actually this accident has nothing to do with Kyshtym town, but completely, let's say, connected with Mayak activity. Here you can see, let's say, the view on Kecha River, and here is the map of contamination due to the wind resuspension of sediments Karachay during the drying period and high winds. All these incidents harmed both human health and the environment, resulting in the relocation of more than 16,000 people from 40 villages and settlements, and causing public opposition towards the activities at Mayak. From the mid-1950s, it became necessary to assign substantial resources and large proportion of the scientific and technical potential towards rehabilitation of contaminated areas. Discharge of radionuclides into the natural lakes and ponds at the Mayak site began in June 1948, when the first reactor started. Water from Lake Kyzyltash was used as primary circuit cooling water for the reactor. Until 1990, this reactor was used as a source of this pond was used as a source of cooling water for all the other Mayak reactors. Therefore, discharges to this reservoir too contained short-lived activation products formed by irradiation of the reactor core cooling water. Production of high liquid waste, however, started in early 1949, when the first batch of irradiated fuel was sent to reprocessing, and the activities of Mayak began to seriously influence the site and the surrounding area. So a number of natural lakes and ponds on the Mayak site have been used as reservoirs for the management of intermediate and low-level radioactive effluents during the operation of the site. These include Lake Karachay. Lake Karachay is over here. The Reservoir 17, Reservoir 3, Reservoir 4. And artificial reservoirs which were created by damming the Kecha River later on. These are Reservoir 10 and Reservoir 11. Here on this table, you can see the inventories of radioactivity, primarily cesium-137 and strontium-90, in the vicinity of Mayak. Of course, the highest inventory is in Lake Karachay, as much as 4,400 petabecquerel. So, routine discharge of intermediate liquid waste to the Kecha River occurred between 1949 and 1956. Liquid waste was discharged into natural pond, which subsequently became part of the system of industrial reservoirs as Reservoir 3. It's located over here. Discharge from Reservoir 3 entered into the next reservoir, which also originally was small natural pond. Reservoir 3 and 4 functioned as sedimentation ponds for contaminated water. In 1949 to 1956, more than 100 petabecquerel was discharged into Reservoir 3. And here you can see the dynamics, how the surrounding area was changing with time. Here you can see the appearance of one more reservoir, which was artificially created for the sedimentation of contaminated particles and to prevent their dispersal furthermore along the Kecha River. And here you can see the next artificial reservoir after the construction, the next dam, again to let's say strengthen the prevention of dispersal of radionuclides along the Kecha River. The total release of beta emitters, a similar order of magnitude, was the similar order of magnitude to those discharged from Sellafield to the Irish Sea, as we were told. That was between 1952 and 1992. However, routine alpha discharges from Mayak were a factor 500 lower than Sellafield discharges. Environmental monitoring of activity levels in Kecha River started back in 1951. Reservoir 3 and 4 played a very important role in sedimentation of radioactivity discharges to Kecha River. 68% of strontium-90 and 89% of cesium-137 were returned in the bed of these two smaller reservoirs. When Reservoir 10 was constructed, the amount of radionuclides entering the Kecha River dropped considerably. The activity entering the river below Dam 10 fell from 50 to 960 gigabecquerel per day to 18 gigabecquerel per day. The construction of Dam 11 made it even more decrease of penetration of radionuclides along the river. Here you can see the variation, spatial and time variation of radioactivity in Kecha River and Iset River water. Here you can see the, let's say, reduction in total beta activity in Muslyumova, which is located in Kecha River, and Pershinskaya, which is located further more on Kecha River. And here you can see the dependence of the total beta activity from on the distance from the let's say input point, and also this is dependence from the time. Here you can see, let's say, increase in years. So discharges of strontium-90 and cesium-137 that occurred during the period 49 to 56 have contaminated 240 square kilometers of Kecha River floodplain with an area of 80 square kilometers, contaminated at levels above 3.7 10 to 10 becquerel per square kilometer, and abandoned to date. About 7,500 people evacuated from 20 settlements along the coast of the Techa in 1953 to 1960, which received the radiation doses ranging from 35 to 1,700 millisievert. Discharges of intermediate liquid waste to Techa River between 49 and 56 in amount more than 100 petabecquerel are now considered as a serious error in judgment. So, Lake Karachay is very well known as probably the most contaminated lake on the earth. This reservoir was originally a small, shallow natural lake and tendency to dry out during the drought. In 40s, it was 750 meters long, 450 meters wide, 1.5 meters deep, and 26.5 hectare in area. Since 1951, the lake has been used as a repository for intermediate liquid waste, replacing the previous practice of discharging the waste into the Techa River. Between 1951 and 2005, 556 megacurie of beta activity has been discharged into the Lake Karachay. Radionuclide composition of intermediate liquid waste included strontium-90, yttrium-90, radiocesium, zirconium, niobium 95, cerium, stibbium, ruthenium, cobalt, as well as uranium, plutonium, and transuranic elements. Annual mean beta activity of liquid waste was 1.2 to 10 to 9th degree to 1.6 10 to 10 degrees becquerel per liter. The radionuclides are distributed in the reservoir as follows: 7% in the water, 41% on the reservoir bottom loams, and 52% on amorphous hydroxide precipitates. In 1993, the strontium activity concentration in Lake Karachay was as much as 70 megabecquerel per liter, and the cesium-137, 100 megabecquerel per liter. Groundwater samples collected in the vicinity of Lake Karachay were contaminated with relatively high levels of strontium-90, up to 9,000 becquerel per liter, and cobalt-60, up to 4,000 becquerel per liter. The source of these radionuclides is infiltration from Lake Karachay with a maximum lateral velocity of 80 meters per year. Samples from the most contaminated well also showed high concentrations of uranium, different isotopes of uranium. Here you can see the dispersal of radionuclides in groundwater of the area of Karachay. Here is the Karachay is located, and these are the aquifer of groundwater below the Karachay. Here you can see the aureole of the strontium-90, and here is the cobalt-60. Strontium-90 and cobalt-60 are more mobile radionuclides as compared to the cesium, so cesium concentration is much less in groundwater. Here you can see the maps of dispersal in groundwater of uranium. This is again Karachay, and these are the isolines of the uranium levels, and nitrates. A lot of nitrates were the very high concentration of nitrates were in the waste, and therefore these are the, let's say, dispersal of nitrates in groundwater below the Karachay. So, attempt explosion of a tank containing high-level liquid waste occurred in September 1957, creating what has become known as a Kyshtym accident. So some 740 petabecquerel was actually released during the accident, but an estimated 90% settled in the immediate vicinity of the explosion site. So these tanks with high liquid waste were quite similar to what Tom shown to us. However, due to exothermal reactions and due to the lack of cooling of this tank, the explosion took place and these liquid waste were released. 74 petabecquerel of radioactivity was released into the atmosphere and dispersed by the wind to form the so-called East Urals radioactive trace of about 30 to 50 kilometers width and about 300 kilometers long in northeast direction from Mayak. And you can see here the large cities around this trace. Yekaterinburg or Sverdlovsk in Soviet time, Tyumen, and Chelyabinsk is over there. Some 15,000 to 20,000 square kilometers received contamination levels higher than 3.7 kilobecquerel per square meter of strontium-90. A deposition of 74 kilobecquerel per square meter of strontium-90 was established as the intervention level for evacuation of the population. This area of approximately 1,000 square kilometers became known as the East Ural radioactive trace. The maximum contamination density was found to be close to the site of the explosion itself and attained levels of 100 megabecquerel per square meter of strontium-90. So here you can see the radionuclide composition of the material released in the Kyshtym accident outside the Mayak boundaries and released activities. So at the time of the accident, 33% of the area was used for agricultural purposes, 20% was forested, and 23 rural communities existed in the area. This population were evacuated, amounting to some 10,700 people in total over 22 months period after the accident. Further utilization of the area was temporarily banned, but in 1961, reclamation of the area was initiated. During the period from April 10 to May 15th of 1967, contaminated sediments from Lake Karachay were dispersed by the wind storm up to distances of 50 to 75 kilometers from Mayak site. An estimated 22 becquerel was associated with this contamination event. Cesium-137 was the predominant long-lived radionuclides constituting this release and may have accounted for 75% of the total radioactive inventory. Most of the fallout was deposited near Lake Karachay, within the Mayak site area. Due to the influence of winds from different directions, the contamination density distribution in the affected territory was uneven, and the boundaries of the affected area showed a complex configuration. The contamination reached a distance of 50 to 75 kilometers from the site. The fallout occurred largely to the northeast and east of Mayak, partially overlapping the central part of the East Ural radioactive trace region. Beyond the Mayak site boundary, the length of this trace was 15 kilometers and width 1.5 to 3 kilometers. Surface contamination of the vegetation and soil was predominant, and the bioavailability of the radionuclides associated with these fallout particles was very low. Thus, both root uptake and the transfer of strontium-90 and cesium-137 to agricultural crop harvest and cow's milk were relatively low. Compared to the transfer coefficient obtained from the Kyshtym accident region, the transfer of strontium-90 and cesium-137 to the agricultural crop harvest and cow's milk from this incident was a factor of 2 to 10 lower. The radiation and radiological consequences of the incident were assumed to have been minimal. The increase in gamma radiation dose at inhabited locations didn't exceed 40 to 70 microsievert per hour during the initial period right after the incident. And this dose rate decreased with the effective half-lives of about 2 to 3 months. Radioactive surfaces contamination of agricultural produce led to maximum internal doses to the public within the first year being less than a few % of the admissible dose. The radiation conditions subsequently improved considerably, and the background levels were attained 2 to 3 years after the incidents. No observed increase in specific activity of the lake water or in groundwater in this surrounding area was experienced. So now we go to the river system and the methodological approach for the field studies, which combine both radioecological surveys of the whole river system with regular water sampling in one of the critical regions throughout the hydrological cycle, with measurements of man-made radionuclides such as cesium-137, strontium-90, plutonium isotope, and tritium. In 2004 and 2005, Research and Production Association Typhoon radioecological surveys were conducted for the section between the lower reaches of the Kecha River and the point of the Irtysh inflow to the Opt, totally about 1,400 kilometers. So you can see here the whole river system. Here is the Ob River entering furthermore in the Arctic Ocean. This is Mayak, this is the Kecha River, then Iset River, Tabol River, Irtysh River, and Ob River. So the whole river system can be traced for the strontium-90 dispersal through this river. So you can see here just the, let's say, working moments of this radioecological survey using the boats in large rivers. This is the expedition camp where the people stay and have the simple equipment and so on. This is the driving of expedition vehicles through the Russian roads, which sometimes is not really a road, and this is the Kecha River. So the challenge in monitoring of water is that we had to measure radionuclides starting from very high levels in Kecha River and ponds, and till the background levels, which are very low. So for these purposes, we have to use in the field the systems which allow to collect large volume samples of water, like hundreds or even sometimes 1,000 liters. Such system was developed in Typhoon and presented over here. This is a multi-layers filtration system which is quite efficient for the, let's say, large flows. And this system allows to filter the water directly in the field and to take suspended matter on the filters and dissolved radiocesium on the cartridges with normally hexacyanoferrites impregnated materials like fibers or cellulose or so. And here is the system which we actually, this system was developed back in 1970s, 1980s, and was used for oceanic waters as well as for surface waters. So here you can see the results of monitoring of strontium-90 in Tabol and Irtysh rivers in the region of their co-influence. And you can see here how the, first of all, we can trace Mayak strontium quite far away from the Mayak itself, where the Tabol River enters to Irtysh River. And we can see here how the natural dilution influences the concentration. This is the point in Tabol River mouth, and this is the strontium which is brought by Tabol River from Mayak. And this is the concentration in nearby, but in down in Irtysh River after the entering of Tabol. You see the tremendous decrease of the concentration. Of course, we have here. And this is the scheme where the Tobolsk is over here. And this is Irtysh, and this is the and this is Tabol, which is taking the radionuclides from Mayak side. This is also an interesting picture which shows the impact of Mayak radioactive waste transport, and that this transport is distinctly traced by strontium-90 as far as the area of the Irtysh and Ob confluence, which is even farther more than previous site. So this is the let's say distance from the dam 11, where actually the let's say protection zone ends. And we see how this strontium is diluted by the waters of this river system. So when we move furthermore, new tributaries join and they dilute the strontium, and actually strontium falls down to background levels in here in Opriva. So remedial measures which were taken in the southern Ural contaminated areas. They started in 1951. Firstly, a series of dams were constructed to create an enclosed series of lakes isolated from the rest of the Kecha River with canals to the north and south to divert the uncontaminated river water. By 1960, about 7,500 people were evacuated from 22 villages in the upper reaches of the Kecha River. An exclusion zone was created around the Mayak site, including the lakes reservoir and the Asanov marshes, where significant quantities of radionuclides were retained. So here again you can see the, let's say, historical dynamics, how these countermeasures were taken and how these additional reservoirs were created to settle the particles from contaminated particles. So further long-term measures were introduced to reduce the exposure of people living in settlements on the banks of Kecha River. Floodplains were fenced off and the access of people and livestock to this area was restricted. Restrictions on drinking water and fishing in the river were also introduced. Construction of wells and pipelines to provide uncontaminated drinking water started in 1953, and by 1954 all inhabitants and cattle were provided with water from other sources. However, some consumption of river water was thought to have continued until 1956, when further measures were taken to enforce the restrictions. These long-term measures are still in place, although there is evidence that villages do not always follow the restrictions, sometimes fishing in the river or letting the animals graze the floodplain. The priority for current and future actions is to prevent further contamination reaching the occupied area by taking various remedial measures within the restricted area. However, consideration is also being given to reducing exposures on the river banks downstream, so measures such as removal of the top layers of sediments or by shielding the contaminated sediment with crushed rocks. So remediation of Lake Karachay and surrounding area. So between 1967 and 1971, remedial work was carried out to cover the lake, to fill in shallow areas, and to recultivate the area around the reservoir. The shoreline was reinforced by banks of rocks and some 570,000 cubic meters of soil and 12,000 cubic meters of gravel and 9,000 cubic meters of rock were dumped into around the Lake Karachay. This raised all the banks and substantially reduced the water surface. Further monitoring of reservoir included strict control of the water level. If the water dropped below the minimum permissible level, clean water was to be added into the Lake Karachay. Despite these measures, Lake Karachay was still a source of potential atmospheric contamination. Should, for example, a whirlwind occur, it could disperse radionuclides over the large area. it was decided to cover the whole reservoir and immobilize the loose bottom sediments. From 1978 to 1986, a method was developed by which Lake Karachay would be filled in with hollow concrete blocks and crushed rocks. From 1986, the operation to fill in the reservoir has proceeded according to 3 stages. So maybe I skip these stages and just say that the surface of the Lake Karachay decreased substantially during the time, and in November last year the Lake Karachay was completely covered, and nowadays this lake does not exist anymore. However, the groundwater contamination is still there, and this is the main concern of nowadays, because the groundwater are very severely contaminated. This contamination disperses, and therefore this area should be under control. So the main messages of my talk are the dispersal of radioactive materials from Mayak to the environment led to harmful effects on the environment itself, restriction on land application, relocation of inhabitants from a number of settlements, and observed health effects on human population. The radionuclide of main concern is strontium-90, as it is remobilized from soils and sediments to much greater extent than radiocesium and plutonium. Increased contamination of groundwater, in particular strontium and cobalt, from Lake Karachay is of serious concern still nowadays. To avoid the transport of contaminated water down the Teche River, huge reservoirs were constructed in 1956 to 1963. A rehabilitation program to fill in Lake Karachay has been completed in November last year. The surface area of the lake has been reduced from 0.51 square kilometers to 0. And now I thank you very much for your attention.
ありがとうございました。Thank you very much. では、質問、それからコメント、ある方、挙手お願いします。はい、こんなことお願いします。
貴重な講演、どうもありがとうございました。汚染の、大きさもさることながら、この下流への影響というのが調べられているということで、非常に興味深かったんですが、具体的で、ストロンチウムの下流、そうですね、はい、この図なんですけれども、これはその流量のから見て、これ単純に希釈したと見てよろしいでしょうか。それともやっぱり、蒸発等で例えば何十%かロスしたりとか、何かこの濃度と流量の関係みたいなものは何か分かったことはありますか。
Yes, of course, this is all monitored, and moreover, in last years there were a number of works on modeling of the transport of radionuclides through this river system, taking into account the flow rates, the weather, the meteorological conditions, and so on, all the hydrological stuff together with the radiological. Yeah, but this is not only dilution, of course, because this is the flow of radionuclide, which is simultaneously sorbed and dissolved by bottom sediments and suspended matter. So we should consider all these systems, let's say, separately and in connection to each other. So the suspended sediments go with the flow. They, let's say, in contaminated, where the water is contaminated, they sorb the radionuclides from the water. When they go further and clear water is diluting, so this suspended matter will release or remobilize the cesium or radionuclide in general, will transfer from suspended sediments to the water column. The more conservative role, but still very important role, is belong to the bottom sediments, because the water flow, of course, is interacting with the bottom sediments and also desorption. So the kind of retardation, of the river flow takes place. But what is important, that actually the trace we can see with the strontium, the most mobile radionuclide. We can't see such a trace with the cesium. There is a lot of cesium in Kecha River and in the Kishtim accident area. But cesium doesn't move with the water. It's settled, it's bound with the particles, settled, and then buried on the bottom. But strontium is moving because of its specific properties, because the KD value of strontium is low, and so mobility is high, and therefore we can. This is not like pure, let's say, pure dissolved element, like tritium, for example. Tritium just goes with the water flow. Strontium is not like tritium, but still much more mobile than cesium. And therefore, we can trace strontium till Ob River, actually till the Arctic Ocean, from the site which is located strongly in the south. So this is complex process, a process with retardation due to this sorption, desorption, and let's say some fixation, but still mobility of radionuclide is very important in this sense. Is that answer?
Yes.
Okay.
ではお願いします。
この図に関連してなんですが、もしデータがあったら教えていただきたいんですが、ウォッシュは水だけじゃなくて、ウォッシュアウトでこの地域全体汚れてると思うんで、そのウォッシュアウトによる影響は最初何年ぐらい続いたのかとかっていうなんかエスティメイトというかデータがあったら教えていただきます。
Yeah, sure. A wash-off from contaminated areas is also considered, and as I told, the floodplain of Kecha River is extremely highly contaminated, and it contributes. But still, the main source of the strontium is infiltration through the dam body, infiltration through the bottom of these reservoirs, And this makes a major input to the strontium balance in, let's say, lower reach of Teche River. Wash-off, of course, contributes, but this is not the major inputs in this system. Sometimes wash-off is the main. For example, here wash-off is very important in Fukushima area and so on. But in Mayak we have, let's say, other sources important, which is the liquid waste, which were direct liquid waste to Teche, and this radioactivity was accumulated by bottom sediments and so on. And with the time, this is still, let's say, remobilized from the bottom sediments. Okay.
他にありませんでしょうか。
Thank you, Alexei. Nice talk. You mentioned health effects. Could you expand on that a little? What have health effects to humans or the environment? Have they been documented?
Yeah, they have been documented, but you know, I'm not a health person. I am familiar with this just because of publications and so on. I would address you to other literature sources I can share with you later on, but I would not, let's say, interact on this sensitive issue, which is I'm not expert in. Okay?
Thank you.
はい。他にご質問ご意見ありますか。では私から一つよろしいでしょうか。先ほどの恩田先生の質問に少し関連するんですが、途中でもセシウムの測定のためにろ過をして溶存体と溶存種とそれからパーティクルとして存在しているものと分けて測定していらっしゃいましたけれども、それの経年変化、経図変化のデータをお持ちでしたら見せてください。というのはよくご存知のように福島の場合はほとんどが、事故の直後は溶けているセシウムも多くだけれどもその後にはすぐ粒子にくっついているセシウムの方が多くて、ただこのような土地ではとても肥沃な土地で有機物もたくさんあって溶けているセシウムの濃度もずっと高かったと報告がされていると思うんですけれども、実際にどれぐらいの割合で溶存種があったのかというのがあれば教えてください。
So, as I told already,
ごめんなさい。
no. Can I? Okay. Cesium is strongly bound by particles, especially by clay minerals. Here we monitor cesium also together with strontium and so on. And I just decided to show this picture about the monitoring of cesium because I know this filtration system is very popular now everywhere and also in Japan. But actually in this river system we observed background levels of cesium which are determined by global fallout, nuclear weapon testing. So after the definite distance from, let's say, Mayak, we actually don't trace cesium coming from the Mayak because it's bound before and settled. So then here in Fukushima, you are very lucky because you have here a lot of clay minerals in the rivers, and you have very low proportion of radiocesium in dissolved form. Most of your radiocesium is bound to the particles, and this is good in terms of, let's say, mobility of radiocesium and bioavailability of radiocesium. It still doesn't mean that cesium does not move. Cesium moves with the particles. So with the suspended sediments, with the sediments during the extreme floods, and so on. So it still moves, but the mobility and bioavailability of radiocesium in your case is lower as compared with, let's say, Chernobyl case, and similar to here in South Europe case. Another difference is you have a lot of precipitation. For example, here in South Europe, the annual precipitation is 400 millimeters. Here in Japan, in some places, you have 4,000 millimeters. And precipitation is very important factor, because precipitation forms the runoff and moves the particles and so on. In this sense, you have, let's say, faster attenuation of radiocesium deposited on the catchments, because the wash-off is much faster here due to precipitation, but not only precipitation, also you have steep slopes, you have a lot of mountains, hilly catchments, and so on. We don't have this in our plain areas, and therefore, so these two factors, precipitation and, let's say, slopes, steep slopes, but also you have higher annually average temperature. You never have soil frozen, for example. We have freezing of soil for several months a year. During this time, radiocesium just stuck on the place, doesn't move at all. Yeah, it's for some places in Russia and even in Ukraine, it's 3 to 6 months, not maybe 6 months, but 3-4 months the soil is frozen. Here you don't have, therefore you have more, let's say, more pronounced processes of attenuation, of, let's say, dispersal of contaminants, and therefore, as I say, the self-purification in your case is higher as compared to Chernobyl and even in Ural. I'm not sure that this is answer for your question, but this is what I'm thinking about all the time.
Okay, thank you. Yes. 他に何かご質問。もう一つ。ごめんなさい。じゃあ後ろの方から後ろの方から。
Thank you for your great presentation. So this is gonna be a general question for you. As you know that radioactive will definitely have environmental impact, right? So how far, like, one country can predict the environmental impact that might be happen because of nuclear power? So, like, how far they should prepare for the worst?
Should prepare for what?
For the worst, like the worst, like the bad one.
Ah, okay.
The worst, like the most risk disaster.
Okay. So, as is shown by this comparison of different situations, yeah, with these plutonium production sites and with this accidental contamination. So, situation can be different. So, the general dynamics of the contamination pattern can be different. Attenuation can be different. Self-purification can be different. But general, let's say, laws of the behavior of radionuclides are more or less known now. And let's say, yeah, this knowledge is more or less established. Of course, this is also interesting to test and to check how really well you understand what's going on. And especially the challenge is when completely different environmental conditions are. Like, let's say, comparison, for example, situation here in Fukushima is very challenging if we compare this to Chernobyl, Euro states, anywhere. But I would say that the main laws of the behavior, they are all the same. And we can explain, let's say, differences in terms of our understanding of the processes which are going on, and in terms of speciation of radionuclides, how they were released, in which forms, and so on. So I think we can predict this more or less in any place over the world. If that was the question.
この生息事故の時に麻薬の事例を参考にその後の調査でですね、麻薬の例を参考にされたというお話があったんですけれども、例えばその特定される例えば刑事の値としてですも多少気候が違いますね、麻薬というで、その2つの麻薬の形質というのを、例えばセシウムとその次のケイジンたちこういったものは多少違いがほとんど変わらないという感じです。
So, first of all, I would say that every accident is very specific. So, for example, Kyshtym accident was called by some people as a strontium accident because the trace was formed mainly by strontium, and therefore the main efforts have been put to the investigation of strontium behavior. In Chernobyl case, we had more or less mixed accident, where both cesium and strontium played important role. However, still, if we consider the closing zone, 30-kilometer zone or near, so both cesium and strontium played an important role. However, outside the closing zone, mainly again cesium was of interest. And therefore some, let's say, agricultural people or let's say European people, they call Chernobyl accident a cesium accident. So in this terms, term, Fukushima accident is again cesium accident because the contamination is mostly formed by radiocesium. Of course, there was a lot of iodine, but iodine is short-lived. And this is another scale of problems, yeah? They influence only relatively short period of time. So in terms of comparison of Chernobyl and Kyshtym accident, I wouldn't say that we found some serious discrepancy in behavior of radiocesium and radiostrontium. But we found differences. First of all, in case of Chernobyl, the fuel particles were released, which were insoluble in water, and but in case of Kyshtym accident, liquid waste was released, and strontium and cesium in this liquid waste were in more or less dissolved form. Actually, this were the operating solutions; they were just wasted, and so that were the solutions of cesium and strontium, and therefore original chemical forms of radionuclides in Kyshtym area and in Chernobyl were very different. But initial speciation of radiocesium, even just in Chernobyl, was also different depending on the distance. For example, in United Kingdom, mostly radiocesium was deposited in dissolved form, so as a condensation particles. But in 30 kilometer zone, 60 kilometer zone, even up to the, let's say, 200 kilometer zone, there were a lot of fuel particles. And this influenced substantially on the, let's say, long-term behavior of strontium, because strontium was first leached from these fuel particles and only then became bioavailable and mobile and so on. Therefore, so there were differences between Kyshtym and Chernobyl, but these differences could be explained from point of view of our understanding of speciation, their kinetics and dynamics, and so on. And also KD values. For example, first measured KD values of strontium in Chernobyl were much higher than in Kyshtym. But that was because of fuel particles, because strontium was incorporated in fuel particles and therefore increased the, let's say, solid phase concentration of strontium. Okay, there is a difference, but we can explain this difference. This means we understand what's going on, we understand the reason, and yeah, there is a difference. But if we, let's say, analyze this from our knowledge, we understand why is it so. But I would say another also concerning the comparison of different accidents. Actually, for us in Chernobyl, Kyshtym was like for Fukushima, Chernobyl, yeah, the previous accident. However, there is a difference. Concerning Chernobyl, we have a lot of publications and so on. Concerning the Ural, we even didn't know that this accident happened, because the information about South Ural was completely classified, completely closed in time of Chernobyl. But we still used the experience of Kyshtym. How? Because people who were involved in Kyshtym accident, they were around, so they had their knowledge in their heads, and they shared. Moreover, a lot of them were, let's say, our supervisors and, let's say, teachers and so on. Such people like Rudolf Alexakhin, Anatoly Tikhomirov, Boris Prister, and so on. So they were involved in Chernobyl, also starting from immediately after the Chernobyl, and they shared what they know. And for us was very important to communicate with these people because we couldn't read the papers, so it was not written. There were publications, but they were very specific, so they couldn't say like they couldn't publish the numbers in curie per liters or something like this. Yeah, so that was also the feeling. Maybe it's not the answer to your question, but again, this is what I'm thinking. Because when Fukushima accident happened, it was 25 years after Chernobyl. When Chernobyl happened, that was about 29 years after Kyshtym. This is very, let's say, similar distance, and so we learned on Kyshtym. Fukushima lands on Chernobyl. I think so. This is my feeling.
いや、とっても重要なお話もありがとうございます。
はい、ありがとうございます。よろしいでしょうか。はい、このプレゼントありがとうございました。Thank you very much.
ありがとうございます。